Anything? Start
Yes,
by
start already.
Yeah. Started already.
Yeah. Okay.
okay, good. Now it's we are now we are in the same place. Okay, nice. Okay, yeah. Okay, thanks. Anyway, we are in the room. So okay, last week, right? Last week, no, I mean not last week. Wednesday. Hmm?
Yeah, Wednesday.
Yeah, I know. I hear someone saying something. Yeah, Wednesday we basically it's a quite heavy. It's a quite heavy topic, basically inverters, right? Inverters actually is one of the most important topics in power electronics. Okay, so inverters everywhere. Remember the typical application is the electric vehicles, right? Okay, so it is needed. So we spend some time on the no, inverters. So yeah, I also received some very interesting questions actually. Yeah. Okay, so today now is to now basically topic 6, chapter 6 is AC motor control. Okay. Now, although the topic actually use AC motor control, but actually we take a look at induction motor only, and more specifically three-phase induction motor only. Now you see the AC motors, right? You have now overall the motors category. You have DC motor, AC motor. Okay, in the AC motor group, you have the single phase, three phase. Okay, we do not cover single phase, we cover three phase. But in the three phase AC motor, you have the induction motor. Then the other popular one used in the electric vehicle is the permanent magnet synchronous motor. So induction motor, three-phase induction motor, three-phase no permanent magnet synchronous motor actually is very similar. Sometimes the same drive, can power both if there is a correct. Now, if the sensing no, the sensing components are correct because when you drive the permanent magnet synchronous motor, you need to know where is the position of the magnet. But for induction motor, actually there is no permanent magnet in the rotor. So basically, the three phase in the stator, the current of the three phase in the stator will induce a rotating field in the rotor. So that's why we call induction. So these two fields, now one is the external one from the stator rotating at we call synchronous speed. Then the other one is the rotor. Now the rotor tries to catch up, but the rotor always run a little bit slower. We call this one a slip. Okay. So I know you will do the electrical machines module. Now I think it's maybe next phase. Yeah, but we need to know this because we have this topic, the motor control. Okay, so that's the overall overall introduction to the motors. Okay, you see here now. See something now. The control of DC motors requires the provision of variable DC voltage. This is interesting. When you control a DC motor, right? Because we don't have experiment in DC motor. You will have it the next semester. That means you can change the voltage. That means you change the voltage applied to the DC motor, then the DC motor speed will change accordingly. Okay, then the AC motor is different. Okay, the AC motor has a number of, okay, that's an advantage. When you control the AC motor, right, you have to control the frequency. It's not the voltage anymore. Although for the general purpose control of AC motor, when you increase the speed, we also increase the motor voltage a little bit. Now we call this is a variable voltage, no, variable frequency, variable voltage control. But eventually, whether the motor, will run faster or not, totally depends on the frequency. Yeah, so the key here is the frequency. Okay. Now you see the AC motors has some advantage. They are lightweight, especially the permanent magnet synchronous motor popularly used in electric vehicles. Actually, the power density is very high. You see the similar size. Okay, now I have some in the lab. Now similar size as the induction motor. Actually, the permanent magnet synchronous motor can be 10 times more powerful. Yeah, but here we cover AC motor, the induction motor. Okay, when we study induction motor, the first concept is this: synchronous speed. Synchronous speed meaning the rotating, not the rotating magnetic field speed. And this one is a little bit harder because first time, to learn the AC motor concept. So this one is maybe a little bit abstract. Now, basically how fast the motor rotates, right, depends on the synchronous speed. Remember that the two, just now I said the difference is very little, maybe 3% only. Uh, uh, Between the synchronous speed, which is the rotating magnetic field, and the motor speed, the speed you can see, you can hear it. Also, the speed that drives the tire. Okay, so this formula, this equation, you need to know now. 120F divided by P. The F basically is the frequency, then P is number of poles. And I can show one example here. Use draw. Okay, for example, my motor is supplied by the utility frequency. That means SP power grid, 50 hertz. Yeah, this one is 50 hertz. And the frequency, the F, 50 hertz. Okay. Then, okay, 50 hertz. Then the motor number of poles actually depends on how you wind the motor. Basically, this is the stator. Say we see the number of poles is 4. That means got 2 pairs. Yeah. Remember, number of poles, always always go in pair. You have North Pole, South Pole, North Pole, South Pole. Basically, when you make the motor, you can decide how many poles you wind. For example, I have a motor. Almost all the induction motors in our lab actually has four poles. That means 2 pairs. Okay, now with these parameters, right, I can calculate the synchronous speed. Sometimes we write a capital letter NS. We just sub into here 120, right, times the frequency 50 hertz, then divided by the number of poles. Yeah, quickly press your calculator. No need 330 cancels. Now you get 1,500 RPM. That's the synchronous speed. Yeah, it's quite easy to find the synchronous speed, right? Yeah, so long I know the frequency applied to the motor, I know my motor construction, the number of poles that I can estimate. Say you want the motor go slower, that means slow down the motor. Okay, that means 50% of this speed. Then easy, you just change the frequency to 25 hertz. Then you do this calculation again, you will find, okay, the synchronous speed, motor speed, sub 25 into here, because 750 RPM. Yeah, so that's how the motor is controlled, the speed is controlled. Then you are, for example, you are in the highway, you drive an electric vehicle, electric car. You want to go as fast as possible. For example, you want to test the car, to the extreme speed. Maybe you can 10 times more faster than 1,500 RPM. Then you just increase the frequency to 500 hertz. Then sub into here, you get 15,000 RPM. Yeah, that's how we regulate the motor speed. Okay, so this one is the synchronous speed. Yeah, actually, it's not the motor shaft speed. Remember, the motor, right? No, the motor eventually, no, it is the shaft that will drive something. So then maybe you have question. Then how fast the rotor will turn? No, very close to this. Usually there's like a 3% difference. Yeah, so it's very close. This one is the rotor, the motor rotating one. now can do work. This one can drive your car, the tire. Now this one is the synchronous speed is due to the applied frequency. Yeah, this one is really the rotor speed. You can hear it. You can hear the humming sound. Then this is also the motor. The speed drives the tire. Now, but okay. By the way, in the electric vehicle application, usually there's one gearing system. That's the speed reduction gear because the motor runs too fast to drive the tires. So you go through a reduction gear. So this reduced speed, basically the speed, high speed converted into torque. Then this torque will drive your electric car. I mean, drive the tires. Okay. So any questions about how to calculate the synchronous speed? Hello?
No.
No, right?
No, sir.
Yes, okay.
120 is the what? 120 is
Oh, 100
the
120 is a constant. Yeah, it's always here. It's a constant. No, actually, this one is
the formula. It's part of the formula.
Yeah, it's part of one. Okay, write the better one. Actually, now the more clearer one I can write here. Now, small letter doesn't, no big, no capital letter doesn't matter. See, NS. Okay, basically it's this. 120 is a constant times your frequency. Still remember the meaning of frequency, right? Then divided by number of poles. It's a formula. Yeah. It's like this. Yeah. So meaning I want my car, for example, or MRT same. Yeah, you want to go faster, you change the frequency. You change the voltage, it doesn't work. You try to pump more current into the induction motor, it doesn't work. The induction motor speed doesn't change much. But when you change the frequency, you apply a different frequency, then the motor goes faster or slower, depends on your frequency.
So the higher frequency, the higher RPM will go.
Yeah, definitely. Yeah. For example, I have the two example, right? If your frequency is 25 hertz, then roughly the motor, turns at this 750 RPM. But if I double the frequency, you also double the RPM. Yeah, because you just start.
100 hertz will be 3000 RPM.
Oh yes, you do a 100 hertz, right? So this one will be 3000 RPM. By the way, the EV motors runs very, very fast. Okay, Tesla Model S and the Model Y actually use induction motors. Okay, the motor can run actually at 20,000. No, I remember it's 18,000. No, around 18,000 RPM, but now can run even faster. You can imagine, say we say the motor runs at 15,000 RPM. That means your applied power frequency should be 500 hertz. It's quite fast, right? That means the quite high frequency. Yeah. So that means you just when the controller receive a demand request from operator or driver or captain, then the motor basically runs following the setting of the frequency.
So, sir, for the synchronous speed, the formula we just follow the NS1, the omega S1 don't need.
Okay. Okay. No, this one is no. This omega. No. Okay. No, this one is the angular velocity. No, angular velocity. No, this one basically the omega one is the. Actually, that is where the two. No, the 120 comes from. Basically, it's times 60. Okay, this one is the readings. Okay. I try to write better. Rad per second. Okay. No,
it's just like it's like a breakup version of the RPM lah. So it's radian per second.
Okay, this one is more academic. No, because when we do other calculations, right? Usually we use the radians per second. But so far in this topic, right, most of the time we use this as RPM. RPM is easy to understand, meaning revolutions, right? Revolutions is already written here actually. REV, yeah, revolutions per minute. Yeah. So actually we can easily convert this one to days. Okay. So now this radians per second, right? Now if okay, one round, now say the motor turn one round, complete round. How much is the angle? Okay, from here then turn one round. This is 360 degrees. Now which is also equal to 2 pi radians. But 2 pi radians actually is one revolution. Is that right? True?
Yes.
Yes,
Mm.
okay. Then we can convert this into revolutions per minute. You see, okay. So this is radians per second. Okay. Then you can tell omega s. Okay. Now if we, okay, now this omega s is called 2 pi f divided by p. Not divided by p, I write down here. Okay. So, okay. Now this is the radians per second, right? So if I if I times 60, now if I times 60, that means I get the radians per minute, isn't it? Right? Yeah, you see, here is the radians. No, I see something because this one can be confusing. Radians per second. No, because there are 60 seconds in 1 minute, right? Yeah, there are 60 seconds in 1 minute. So if I times 60, I get read
其实各国的榴莲相信各具风味哦，消费者还是要依据自己的喜好啊，还有口味来。
Oh, muted. Okay, yeah, okay. So this one you get per minute, is it right? Per minute, these readings. Then, okay, I draw a line here. We forget this part. Okay, then okay, I write down here. Now, 2 pi f divided by p. Okay, times 60. Now this one gives you readings per minute. Okay, now, but how to convert the readings into revolutions? Remember, one round is 2 pi, that's one revolution, right? So we simply divide this whole thing by 2 pi. Then we convert this thing into revolutions per minute. Okay, per minute, revolution, RPM. Yeah, this is RPM. Then we do cancellation now. Okay, that means your 2 pi, this 2 pi cancel out. So you get what? You get, okay, now let me do this. 2 pi, where is it? 120, 2 pi. Okay, now the readings, oh, sorry, it's a 4, my bad. Okay, so 4. So I change this one to 4. Okay, allow me to make change because somehow I write it wrongly. Okay, so this is a 4, not 2. Okay, yeah, so this is a 4. So all wrong. Now here's a 4. Yeah, so I need to use 4. Yeah, this is 4. Now here's 4, right? Yeah, 4 pi. 4 pi f. 4 pi f is like this. Okay, then you can cancel 2 pi. Now this one is 2 times 2 pi. If we do cancellation, right? Now cancel this 2 pi. So here 2 pi becomes 2, isn't it? Yeah. So then you can see you get 2f times 60 divided by p. Now what is this? this exactly 120 F divided by P, right? Yeah, so you get, actually they are saying the same thing, all represents speed. One is in terms of radians per second, the other one is revolutions per minute. You see, I get the formula, right? Yeah, so the same thing. Yeah, so now I answered your question, where does the 120 come from? Actually from here. Okay. Right? Okay. Okay. So now, okay. So this one is the first formula you need to use to calculate the synchronous speed. Okay, synchronous speed. I didn't say I'm not saying this one is the rotor speed because there are two speeds running in the induction motor. One is the synchronous speed, which is determined by the supply frequency. Then there's another one, the rotor induction. Through induction, the rotor will also turn. So the rotor speed actually, usually we use, okay, wait a minute, I get it. Now, usually we use NR. So that's the motor speed, okay. So the motor speed is always a little bit less than the synchronous speed. Yeah, so this is always a little bit less. Then, Dr. Samsi, do you have a number? Yes, I have. Later on, we have numbers, we can tell. Okay, we can see the result, okay. Okay, then for induction motor, right? Now look at here, the other components actually needed. Okay, now, okay, the other one, because just now I said the motor synchronous speed and the rotor speed a little bit different. Now, one is the rotor actually turns slower than the synchronous speed. That's why we get the slip speed. Now, this is interesting. Now, this is slip speed, meaning how much is the difference? Now, this one is the synchronous speed. This one is the motor speed. Just now I use NR. Actually, in these slides they use M. Let me change it to M to avoid confusion. Okay, I try to use the same thing. Now this NM. Yeah. So basically, M means motor, represents motor. Okay. So there's something called slip speed. Now, put it simply, slip speed is the difference between the synchronous speed and the motor speed. For example, now if my synchronous speed is 1500 RPM, yeah, this is RPM. Then your motor turns the NM, the rotor, the motor. That is the one drives the mechanical load. Now runs at 1450 RPM, slower than that. Then how much is the slip speed? The slip speed is in slip. Okay, just do a minus. Yeah, it's quite easy. 1500 minus 1450. So you get 50 RPM. You know, that's the slip speed. Yeah, is that clear? So you see, I summarized this one. Okay. No, you see in the induction motor, there is one speed is called the synchronous speed. Is running following the supply frequency. Then the rotor will also tends to rotate. Okay, if the rotor runs at another speed, no, usually it's lower than must be lower than the synchronous speed, then there's a difference between the two, right? So the difference, the minus, you know, the synchronous speed minus the motor speed, we give a name. We call this slip speed. Now this one is important because later on when we do motor control, right, we have to calculate this one. Is clear? So in summary, what is the slip speed? The difference between the synchronous speed and the motor speed. Correct?
Synchronous speed is the omega slip lah.
Omega, or usually remember you said we can use this one, the NS. Omega, that one is okay, but most of the time we use this one. Yeah, so that's the synchronous speed.
Oh, that's the synchronous speed, the NS. Oh, okay.
Yes. Yeah, NS minus NM. No, usually the one way or another, right? We must know the motor speed. Then I can calculate the slip speed. Or you give me the slip speed, I can find the motor speed, isn't it? Yeah.
Yes.
So yeah, for this one, I know the synchronous speed. I also know the motor speed. I can quickly do a minus. I get the difference, the slip speed. But if you give me the slip speed, okay, 10 for example. Now this one is is another example. Now and slip speed, say is 10 RPM. Then your synchronous speed is still 1500. Then, okay, ask your question. How fast the motor will turn? Just minus, right?
Minus 10.
Yeah, you just minus 10 is 1500 minus 10. Then the motor runs quite fast, actually 1490 RPM. Yeah, so that's the RPM. So that's the meaning of the slip speed, because this one will be used later when we control the motor. Okay.
Yes. Sorry.
Yes.
NS is the synchronous speed. The NM is the
motor speed.
Motor speed. Okay.
Yeah. Okay. I can because we don't have module cover that. For example, right now, see this is your motor. I try to draw this. Okay, now this is the motor. Okay, the power supply is here, 3-phase. Now once you can, okay, no, okay, on here there is a shaft, right? So the shaft actually connected to the rotor. Okay, I try to draw this. See? Yeah. So you have a synchronous speed from the system frequency. Then the motor also turns. So that's the motor speed or shaft speed. We call this one NM. Okay, wait a minute. Okay, make it better. Okay, oh yeah, here. So this one is the NM. Okay, is it clear? Questions about this one?
Yeah.
So you got. Yeah, sorry.
Yes, please.
So in summary, now this is 3 phases, L1, L2, L3, 3 phases. Yeah. So okay, so so now you now roughly the idea is there already. That means okay, when the induction motor is powered by the 3-phase supply, there will be 2 things rotating. Okay, the motor, the rotor, this one is the shaft, right? Then you can see it, you can hear the noise. But there's another one, the synchronous speed. Synchronous speed actually is invisible. It's a kind of rotating magnetic field. You cannot see it, but it is there. Okay, then the difference between the two has a name, slip speed. Yeah, okay? Yeah. This is the slip speed, but sometimes we use do not use slip speed. We use percentage, meaning you do this, you get the slip. There's another one called slip. That's NS. You want to use omega, same thing, no difference. That's NM. Then divided by NS. Also, this is a percentage. So this one is this one has a name. It's called motor slip. Motor slip. Yeah, the motor slip. Yeah, okay, I put this here. So it is here. Now this one. Now it's different names actually. represent different things. So this one, no, this one actually is this. Yeah, so you can tell there are two things, One is the slip speed, another one is the slip. The slip basically is a percentage, right? Actually, we can, from here, we can also calculate the slip. You see here, for example, I still use this, so wait a minute. Sometimes, okay. So if in this case, right, in this example, I can calculate the slip as equal to synchronous speed 1500 minus 14550, then divided by 1500. Then you get a quite small number. Let me see, I have a calculator now. Let me get a calculator. I press the calculator, I can get a number. Yeah, okay, let me calculate the value. So 1500 minus 1450 equal divided by 1500. Yeah, I got it. Actually, it's a 0.033. Yeah. So you can also use a percentage. Then you get 3.3%. Yeah, so this one is the slip. The other one is the slip speed. Now different, these two concepts are different. Okay, I write down here. Okay, now highlight here. One is a slip, the other one is a slip speed, not different. Okay, one is here, the other one is here. Right? So you can tell actually, now if say someone says, okay, my motor speed right now has a slip S, 3.3%. Oh, he's talking about the S, the slip. Then from there you can also ask, hey, what is your motor synchronous speed? Okay, if you say, yeah, motor synchronous speed is 1,500, then you can quickly calculate, you can quickly find without any difficulty, find the slip speed, which is 50. Is that right? So basically they are all, these two parameters, are linked. One is in percentage, another one in absolute speed, RPM, unit. Yeah. Is it okay? Is still confusing?
If question asks pole pair, the pole pair means I want to times two, correct?
Yeah. No, if the question tells you the pole pair, you times 2. But the good thing is, in our examples and the exams, we always give the number of poles. No, the pole pair. Now,
Okay.
if you read article or some other reference, right? You say, oh, the pole pair is 2. Then in this formula, you cannot use 2. You have to use 4.
Okay.
Thank
you.
Yeah. Okay. The induction motor, right, also have no this one is a little bit harder to understand. Have equivalent circuit, meaning this one is the supplied voltage. But by the way, the equivalent circuit is a phase one, per phase one, because here you see you got 3 phases, right? Connector L1, L2, then L3. So you got 3 phases. But when we draw the equivalent circuit, we just draw one phase, per phase equivalent circuit, you see. Now this part basically is the leakage reactance and stator resistance. Now this one is the stator. Now the other part, actually this part is the rotor. Okay. Now here is a magnetizing coil. Remember through induction, the induction motor rotor get the get the current. Otherwise, in the induction motor case, the rotor stator, there's no contact between the two. Now, actually, we have some cutaway motors, because I do not take your lab. Otherwise, I can show you very clear. But anyway, you will learn this again in the next phase. I mean, next stage. Yeah, okay, that's the equivalent circuit. Okay, then, okay, more calculating. Now, based on the equivalent circuit, right? Then we have the mechanical power output and the torque. Mechanical power output actually is this. It's quite long, actually. Now, if this one is tested in the exam, no, the formulas must be given. So this one is the mechanical power developed. Then before we take away the loss, okay, from the mechanical power, you can get the torque. Now that's the torque. Torque depends on the speed. This one is the fundamental formula. Now the motor power is equal to torque times omega. You see now we use omega, right? Yeah. So now this omega is actually equal to 2 pi fn over 60, same thing. So this is the relationship. Okay, now say if the motor power is constant fixed, like 10 kilowatts, then if you don't need a lot of torque, right, then the speed can be higher. If you need a lot of torque, the speed must go down so that the total time, the product of the two is equal to the power of your motor, right? So this formula is very useful if you drive right. Okay, you are driving faster. That means now if the road conditions are good, the torque is very little, then your car can go very fast like highway. Okay, so basically these are three variables, they are related to each other. This one is the torque, angular velocity. This one is the motor power. Okay, so you can see actually this formula bridges the electrical engineering and the mechanical engineering, because here is in watts or kilowatts, but here is Newton meters. Now this one is revolutions per second. No, radians per second. Radians per second, Newton meter torque, they are all mechanical parameters, but here is the electrical watts. Yeah. So this watts eventually can go here, then you can do calculation here. But anyway, now if this part is tested, now the formulas must be given because it's too many. It's very hard to, if possible at all, to remember them. Okay. Then more so-called derivation. Okay, now sometimes consider the some values are small, we can remove something, then eventually you can get the simplified per phase equivalent circuit. Simplified, yeah. From here we can start get something interesting, more interesting. Yeah, you see the from here you can tell actually the torque. Wait, let me see the torque. Okay, so the torque, right, is related to your motor speed. Now, but here's a slip. Now, slip into here. Then also depends on the rotor resistance. Yeah, this is a quite long one. No, I mean not very long. Not this many variables, but quite few variables. R2 is the rotor per phase resistance. Vs is a supply voltage. Then the slip is the motor speed in percentage. Then the omega s is the angular velocity, right? Then sub into here. But anyway, we can sketch this. If we sketch this, we see something like this. So this one is the torque speed characteristic. Okay, meaning when the motor is not running, meaning the slip is 1. Is that true? Motor is not running. The slip is 1. Now let's see why. Now remember your slip is equal to ns minus nm divided by ns, right? When the motor is not running, meaning the m is 0. So this ns over ns is 1. So that means the motor is not running. Cannot confuse this one with the speed. This one is the slip. Now it's the percentage difference between the two speeds, the motor speed and the rotation, the synchronous speed. Then when the motor runs at synchronous speed, then the slip is 0. Yeah, because there's no more difference 0. But when the slip is 0, the motor also lose torque. There's no more torque, so the motor will slow down a little bit. Okay, now you look at this torque speed characteristic, right? So this one is the starting torque. Now this one is the peak torque. Now, if your load, for example, your mechanical load, I draw oh no, should be a straight line. Oh, wait a minute. I want to draw a straight line, you know. Yeah, so if you're, okay, this right, got not bad. Now, if this one is your mechanical torque, Tm, so the motor speed will be around here. So this one is the motor, the rotor speed, the shaft speed. Now this little bit here is the synchronous speed. Yeah. All right. So if your torque is a little bit bigger, so it's here, then the motor will slow down a little bit, but not that much. So you see that the speed is very similar to this, right? Yeah. So they are very similar. Actually, my drawing is a little bit biased. The motor speed doesn't change much. Okay, so with the motor torque characteristic, then with the load demand, the torque demand, we can decide where the motor, now what is the rotor speed? Now the intersection is the rotor speed. Okay, so basically that's the fundamental concepts of induction motor. I'm not very sure, maybe you have some questions. I can pause here for a minute or a few seconds, then you have any question to ask me. So this part I think is new, isn't it? Is it new? Questions? I want to invite questions. Any questions? Yeah, this is the motor speed. Here is the synchronous speed. Yeah.
So for the mechanical power output, the formula that is important is finding the power first, right? The power only, right? Then the motor power, right?
Yeah, basically, say you know the motor power, then you know the torque, right? Then you can tell how fast the motor turns. Yeah. So the longer one, now there's not, look at this one here. So this longer one, you get, where is it? It's here. Yeah, based on this, the longer one, basically we just know to get this equation in order to draw, to sketch this. Yeah. So if we know, we can through the derivation, through some calculation manipulating the parameters, then we can get the formula here. Then if you draw this, right, you sketch this to a graph, then you see this. Yeah, so you see this.
So the formula, the constant is the 3 times I 2 times R2 over.
You mean this formula, right? The equations.
The previous one.
Previous one.
Previous one. The top
Six.
developed.
The top developed.
Yeah.
Top.
So the one you underline, that is the formula, right?
That is.
Okay.
Yeah, it's a formula, yeah. But in this case, actually your no, this one is the rotor current. This one is a variable. The speed is also a variable. And so it's S. So the constant is 3 and R2. Now look, once you buy the motor, right, the rotor resistance is fixed. Yeah. For example, what is the material they use, the copper material, then no, this R2 is more or less fixed. Yeah. So this one is actually the intermediate one. No, here is the intermediate one. Now with this, right, we can get the final one here. Now this is the final one. Yeah, but then what is the purpose of this one? We want to draw the torque speed characteristic. Yeah, but for no, this will not. No, I mean, the question will not ask you to sketch this because it's very time consuming. Now you need a lot of time to draw this one. Yeah. So no worries. So this one basically is to show, okay, if you have an induction motor, your torque speed will have this kind of relationship. So the x-axis, now the vertical one is torque developed. Then the horizontal variable is the omega m. Also Nm is the rotor speed. Yeah. So basically, okay, when the motor is not turning, this one is the starting torque. Yeah. Then because the starting torque is larger than your mechanical load, so the motor will pick up speed, then reach the peak torque, then the torque goes down again, then settle down here. Yeah. So it's a person. That's why you turn on induction motor. Actually, you can hear some sound like humming sound, then pick up speed, then slow down a little bit. Yeah. The next time in the lab, you try to listen to the motor speed. You see, you can hear. Okay, at the beginning it's very fast, then later on slow down a little bit. From the noise, you can tell. Okay.
Sure.
Yeah.
So if let's say the question asks need to find the rated torque of the motor, I use the page 3, the torque equals to Pm equals to omega, right? Correct or not?
You mean this one? Yeah, you use this
Right.
one.
If
You're
I
right.
want to find the rated torque.
Yeah, from here. No, this one. That means you.
All
no,
right.
yeah, you will be given the rated speed and the motor motor power. Okay, actually this one is the mechanical power before the losses. Then from here, now if you have power, you have the motor speed in terms of readings per second, then you can find the torque.
So we know that power is I times R, right? Right.
Yeah, power is
for this formula, so is basically to find the motor power is 3 times I, then the 2 is what? What is which one? How to understand that one?
Yeah, okay, you're right. You see the torque per phase. You see we start from I square R divided by S. No, correct, this is true. Actually, the power developed actually is from here. Yeah. So this one is from the equivalent circuit. Yeah, basically we know this part. Okay, I square. You're right. I square R is the power consumption, is also the motor power times R2 divided by the slip. No, this is the power developed. Yeah. So this is here, and then I square R2 divided by S. So you cannot do I square times R. No, it's not enough. You have to divide by the motor slip. Yeah, because the power developed, right? When the motor is running or the motor is not running, the value is different. Yeah.
Okay, so the I square I2 and the R2 over S is the power developed lah.
Yeah. Correct. I2 is here.
Not power developed, power motor lah.
This one is to power the motor, to power the shaft.
Motor power. Okay.
Basically, it's to power the shaft because you see you have other powers. Here also power consumption, some power, but they are useless because they are all losses. Now, what you need actually is the power. Oh wait, I draw a better one. Now, what you need actually is the power on the shaft. That's the one. Is that right? Yeah, that's the one you need. So that's the power on the shaft. Basically, now this power can be used to drive, for example, a fan or drive some car, also okay. Yeah, so that's the power. Yeah, correct. So this is the power developed. Yeah. Now, why we call this develop? Because why we don't say net power? No, because when this rotor turns, right, there are some, you remember the friction, some environment losses. So you have to take away the losses, then you get the net power output on the shaft. Yeah. So which will be smaller than this, no, less than this a little bit. Usually nowadays, the high efficiency motor is like very high efficiency, 90 something, 90 plus something. So the loss is very little. Yeah. Okay, no worries. Now later on, I think that I try to use an example to clarify all the to make all the concepts clearer. Okay. So, so basically we covered the basic motor principle, right? But actually it's very little. No, it's a, you know, in the motor study, right? The induction motor theory actually needs 3 to 4 weeks. That means 3 to 4 lessons, you know, to fully cover it. Yeah. Okay, never mind. So we know the basic, at least, okay, in summary, at least we know there's something called sleep speed, right? That one must know because later on we use it. Yeah, sleep speed. Then there's also a synchronous speed, there's a motor speed, there's a power developed, right? Then with this, actually, we are ready to look at the motor control in a more detailed way. Okay. All right. Shall we go to the speed control here? We continue with the motor. Yeah, some theories, you know, it's not really very straightforward, you know. Okay. Okay, next one, speed control. Actually, motor control, right, to a very large extent is about speed control. How do you run your motor? Go slower, go faster, and how do you regulate? Okay. So there are different ways, you know, but here we cover the fundamental. Now here there are two methods. Now one is the variable terminal voltage control. Now this one can regulate the voltage very little. Now later on you will see some, I think there should be some diagram, very little. Then the popular one is change the frequency, the frequency control. That means we change the frequency, then we can see how the motor will follow. Okay, now you look at this one. Now here, this one is the motor speed control by applied voltage. You know, that means we change this voltage Vs, then we see how the motor speed will change. It actually change very little. You see the torque is not a constant one. It's proportional to, no, it's a function of the speed. So you see when the voltage is very high, the speed is here. Oops. Okay, now when the speed is when the high voltage is here, now this one is the highest voltage. That means we are reducing the voltage, you know, from here down to here, then reduce the voltage further. You see, at the rated voltage, right, the highest one, then the motor speed is here. Now basically you draw a line down to here. Now that's the speed. Speed is here. Then we reduce the voltage significantly. You know, you see like looks like a 50%. Then your speed goes to here. You see, change very little, isn't it? Yeah. Then we lower down more. Then you get this speed. And so the speed. So basically, the diagram tells us, okay, now you want to change the motor speed in a significant manner. So you cannot change the voltage only. No, that one doesn't work. It works, but you can only affect the speed a little bit. Yeah, so we can tell from here. So basically, this one we change the applied voltage. Speed will slow down, but not that much. So the best way actually is to control the frequency. Yeah, control the frequency, meaning you change the applied frequency. Okay, how to control the frequency? Remember, we use inverter, is that right? Yeah, you see the now, for example, the square wave inverter, right? So if the square wave voltage looks like this, okay, now this is the one frequency. Then if I have another one looks like this, okay, yeah, guess which one, now if we use this to drive the motor, which waveform will produce a higher motor speed? The lower one, right? Yeah, because the frequency, you know, for example, the period here, now 50 hertz, right, is 20 milliseconds. I'm talking about 50 hertz. Yeah, but here you have a 10 milliseconds only. So what is the fundamental frequency here? This one actually is 100 hertz. Yeah, this one is a 50 hertz. So you can tell actually in this narrower waveform actually can drive your motor to run faster because this one, these frequencies are 100, this frequency is 50. Why is that? Remember the 120 times F over P. Yeah. Some say, yeah, no, your one is not sine wave form. This formula is for sine wave. But doesn't matter. We have the fundamental voltage actually is the frequency of the period is the wave you applied. Is that right? So that's how we change the frequency. We change the applied voltage frequency. How do you change the frequency of the applied voltage? We tell the inverter, hey, you switch faster. Then I want to make my motor turn faster. So the control circuit will send signal. Basically, is a driving circuit that make the switching faster. That means the waveform looks denser. Any questions?
No.
No, okay. No, okay, fine. Then we go to the next, and now slowly we will go to get to the heart of the speed control. Okay, now this one is the something. This one is the formula derived from there. Okay, I just say the conclusion. Okay, the conclusion is this, because it's quite involved. You have to do a rearrangement of the equation that eventually you get this conclusion here. Where is it? Yeah, we get conclusion now. VF constant. Yeah, that means when you change your frequency, right? You also change your when you change your frequency, you also change the voltage. So I make the ratio constant. So this one is called this control method, right? It's called variable frequency volts hertz control. That VS control. Sometimes you call the variable frequency, variable voltage, variable frequency. Also the same thing. No, something is this the only method to control speed? No, this one is the general method. You use it, it works, but may not give you the best performance, because the best one actually is modern control, like vector control or torque control is a different concept. Okay, so we know this. Okay, now when I control the motor speed, right? For example, I increase the motor speed, then you have to increase the voltage correspondingly. Yeah, that means don't keep the voltage constant, because that will cause saturation and the motor loss will become sometimes can become very significant. So that's why we call this one is the variable voltage, variable frequency control. That means when I change the frequency, right, I also make the voltage higher a little bit. Yeah, so that's the meaning. Yeah, for example here. Yeah, so when I do this, right, I make the voltage higher. That means it's a variable frequency, variable voltage. Okay, some say, oh yeah, I still don't get it. Now, what is it? Okay, we take a look at one example. I think it's not here yet. Later on somewhere. Okay, but here basically we can also draw this to a graph. You see, when this one, okay, the frequencies here. This part is a little bit theory, a little bit harder. So this one is the frequency. Now frequency, right? No, this is also frequency. But we know actually the frequency, the F5 is the lowest. That means the motor will run very slowly here. Now you see the speed? Yeah, if my frequency is the lowest, F5. But if my frequency is here, F1, see the motor will run here. Can tell, obviously the motor speed actually faster than the lower speed, right? Now assume the load is constant. That means you see here, I change the frequency. Actually, I can change the speed, isn't it? Yeah. So this is yeah. Go ahead. Yeah. Go ahead. You say something. Okay. Yeah, I agree. This one looks quite abstract, but no worries. Later on, we do no. Today I try to also go through some tutorial examples, then make the concept clearer. Okay. So there with a lot of assumptions actually. This part now, if you read right, it can be quite challenging. Yeah, quite challenging. Yeah. So basically, this part says okay if your slip frequency is small, so you see the linear one. You see the linear. It's actually your motor speed now proportional to the slip. Yeah. Okay. So we know this theory. The next we take a look. Basically, why no? Okay, question. Why the motor speed control looks like this? No, the variable frequency, but the condition is the ratio of voltage and the frequency should be kept as a constant. Now constant C. So this one should be constant. Yeah, actually it's already here. So you get this. Okay. Then why is it like this? Not through the math equation. Now we do this, then we know. Yeah, we can get there. Okay, then let me see the okay questions. No, I don't. Maybe you don't have questions yet because this part is all about theory, right? Then hello, any questions you want to ask or you want to have a discussion about something? Yeah, maybe you feel this part is boring. Yeah, indeed, the theory a little bit boring. But next, now you have to pay attention here. Now this one is an example. Hello, are you all with me, right?
Yeah.
Yes,
Yes,
yes.
Yes,
great.
yes.
Yeah.
Of course, what is important is what is
Yeah.
real versus
Okay.
Yes, 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 yes.
Yeah, okay. Then okay. Then we take a look at one example. You see, I talk about theory, how many pages? Like 8 pages theory. Then some maybe wonder, do you have an application? How do you crack the numbers? Now here's one. Now you see, a 3-phase induction motor. How many poles? 4. What is the rating? 11 kilowatts. It's not very big. Actually, the EV, right, electric vehicle, the very popular one, like a small one, 4-seaters, can be easily 100 kilowatts. Yeah. So this 11 kilowatts is not very big, but larger than the aircon. Now, air conditioning system, I think I remember one drives 3 like 7.4 kilowatts. I just give you some physical comparison of the different equipment. Okay, what is the terminal voltage 415? Yeah, I remember in Malaysia, the rated voltage 3-phase is 415 volts, right? Yeah. Then frequency 50 hertz, a star connected induction motor. That means no inverter. No, there's no inverter to control the motor. That means we don't change frequency. Okay, we don't change frequency. Now, if we do later on, the question will say, how do you change the frequency? I think this one, yeah, okay. Now for the first part, not yet. Okay, the motor has the following parameter: X2 and the R2. They are the parameters from the rotor. XM is the excitation winding. Basically, is the stator. Okay, let's see what question they ask. Then stator impedance negligible. Stator impedance basically is R1. R1 is negligible. Okay, the motor is driven by an inverter. The motor is driven by an inverter. They operate with the ratio V over F constant. Yeah, that's the VF control. V over F is constant. Yeah, constant. Okay, so that's the control method. We cannot do other control. Other control involves more calculation. Okay, then the question asks you calculate the output frequency and the voltage of the inverter. It's a very interesting question, isn't it? I give you this motor. I give you some parameters, electric parameters. Then I tell you the load, now 50 Newton meters. Then you tell me how to set the inverter output frequency and the voltage. So that's the question. the theory I use to control the motor is V F with V over F with a constant ratio. Okay, so that's the question. No, without looking at without reading the answers, right? This seems can be quite hard. Okay, then let's see how to do it. Now, basically, you sub everything into here, TD, then, okay, this one is a long formula, isn't it? Yeah, a lot of parameters in it. Do you like it or not? I believe you don't like it. Yeah, so this one is a lot of parameters here. Yeah, so basically, so you have to sub the values into here. Okay, let's do it. For TD 50 Newton meters. Okay, this one is important. What is the ratio of VS over F? Oh, we can find it from, no, this one is the phase value. Okay, by the way, phase voltage. Then we can find it from here, you see, 415 divided by square root of 3, you get the phase voltage, right? Then, no, excuse me. Then the phase voltage, right? Now divide by 50 because at rated condition, these are all the rated condition. From the rated condition, I can get the V over S, the VS over F number. Now basically you press your calculator, you can get a number. But here, we leave it here. Now basically, there's no further calculation because we want to, now we are going to bring this number into here. Actually, the whole thing here and how much I can press my calculator 415 divided by square root of 3, then divided by 50. Okay, let me see how much I get. Yeah, I can do the number 415 divided by square root of 3 to get the phase voltage, then divided by 50. I got it. So this one, the whole thing, right, gives you 4.79. You see, that's the ratio. Yeah. So basically this whole thing here. Now you see that the whole thing here. How much is it? Is this. Then this one I cannot. Yeah. So we can get this value. Okay. Then then from here we can use the equation. We sub the values into here. 3.2 constant, not much to say. Number of poles 4. No question says 4 poles in here. You see 4 poles. A number of poles is 4. I just submit. Then time, now basically this formula. R2 is how much? 0.35 also given. Then the ratio VS over F, I get 4.79, which is this. Then divided by 2 pi is 3.14. Then times, this is interesting, SF. Now SF together is a variable. These are unknown. Now that means the slip times frequency together. We are going to solve this together. Now this as one variable. Okay, so now you have to rearrange the equation now to do cross times and so on. Then find you have this equation. Yeah, solve this equation. You get the SF, which is how much? Which is 0.8 hertz. Yeah, so. Yeah, 0.8 hertz. 0.8 hertz meaning, okay, let me try the 0.8 hertz. Yeah, basically you no need to say 0. Okay, so here you get this, right? Get this, you get the whole thing here, but do we have a slip? Let me see, this one is 108, as cannot be higher than supply frequency. Oh, this one give you two values, Now you solve for this, right? You get this and this. Now, because it's a quadratic equation, remember, this looks like this ax squared. Oh yeah, that's a bit mess. Plus bx plus c is equal to 0. How many roots here? You got 2, isn't it? Yeah, so you solve this, right? You got 2 roots. Now one is 169.8, the other one is 0.8. Okay, then we have to decide which one is the correct one. You have to say, okay, slip frequency cannot be higher than the supply frequency. True, because remember the slip frequency is the frequency actually roughly speaking is on the rotor, so it cannot be that one. So this one is out. You have to choose always, where is my mouse? Always choose the smaller one. So that's the answer. Okay. Okay, once I get the frequency right, I can correct the value here. Now you see, but don't forget the slip times the frequency, you got this. Then from here, that is equation 6.3. You need to find the slip speed. This is important. Yeah. So basically, slip speed is equal to 2SF divided by P, 2 times 0.8. Oh, I got this 0.4 RPS, revolutions per second. Okay, RPS. Okay, so this is the slip speed of the motor operating from a 50 Hertz supply. But this one is not RPM, it's RPS, revolutions per second. Yeah, so that's the slip speed. Okay, now remember the question asked you, it's quite a long one. The question asks you what will be the output frequency and also the voltage, right? So we have to find the frequency. Now the slip RPM is not okay. Now we need to get the frequency, which is deliver same torque but different frequency. Okay, so this is the slip speed of the motor operating. Okay, at this. Okay, now the next line is useful with the motor delivering the same torque but at different frequency F1. Its slip speed will remain constant. Okay, now this conclusion you have to remember. That means when you change the frequency, right, the slip speed doesn't change, always constant. Yeah, so will remain to be how much? 0.4 RPS in this case. Okay, with this, right, we can find the speed. Okay, so from here, then we do something. Now, because your okay, so you have to convert this RPS to RPM now. Yeah, so this is the RPM given the motor. Where is it? Okay. Okay, see here, this part is quite tricky. Given the motor speed M1, now that is the no, because the question says you run at this speed. Then given this, right, you can get from here actually, wait a minute. Yeah, so this one a little bit long. Yeah, so how come I didn't get the pen? Oh, no, why stubborn? This. Oh, yeah, I got it. So now given the motor speed, 500 RPM. Yeah, 500 RPM is here. Now, where is it? 500. Where's the 500? But yeah, it's this one. Yeah. You know, the 500 is given actually is here. So given this, right, from there, we can find the difference. Yeah, because okay. Now this question actually we are using the revolutions per second. Later on in the tutorial, we use the revolutions per minute. It's more straightforward. But anyway, from here you can get the synchronous speed. Now remember, just though the theory says that this one is constant, doesn't matter what frequency you use. Then the slip speed now in revolutions per second is constant. So from here, right? Now you convert this one to this and these are the same. Okay, yeah, same. So from here I know the synchronous speed in S1 should be the motor speed plus 0.4. You get the RPS, revolutions per second. Then from here we can tell the frequency. Now this one is a formula. Now NS1 synchronous speed is equal to 2F over the number of poles. This part is no, this part the question is quite hard actually. So divided by P. So from here you can tell. Okay, Now, if this is the case, right, your inverter frequency should be 17.4 hertz. Yeah, so that is the requirement from the inverter. Then Banok answered, but the inverter also, yeah, fine. No, that's the frequency I said. Tell me what is the voltage? From here, now remember the ratio is constant. So from here, you can tell now your voltage should be lower down to this. Yeah. So now the setting is all, no, the settings are all calculated. So you go there, set the inverter frequency 17.46, then the voltage 83.67, three-phase voltage, the line voltage times square root of 3. Then your inverter will meet your requirement. What is the requirement again? Let's see here. You see, output frequency and the voltage of the inverter. Okay, class. Actually, no, I mean, okay, no. It basically it's a quite long one, isn't it? Do you agree? Yeah, but it,
crazy.
huh?
So long
Yeah,
Very
it's
hard,
very it's a very long one. But through basically it's all about, you know, by the way, now if there's a question like this in the exam, right? The form, all the formulas must be given. Yeah, otherwise cannot do. Okay, fine. So this is the the speed control. Remember the control method is what? V over F is constant. Okay. Okay, never mind. This part may be hard. Okay, then you look at this. Actually, when we no, I mean the calculation may be hard. Then how do we do this in the real world? Okay, actually in the real motor control, right? If we use the V over F constant, we call it the variable frequency variable voltage control method. Now, in the real scenario, right, actually you have to do some modification. You cannot follow exactly that one. No, that's the curve. This one you must understand. Okay. No, we may ask you to explain this. Okay. So the real case now here's the motor. Can I really use the constant frequency control throughout the range of the speed? No, the answer is no. Now from here, this region, yes, you can do the V over F constant. Basically, it's the linear part. Okay, let me draw this one more time. I remove it. Yeah. Now this one you must know. Okay, now I say it must know. That means you will use it in the test. So between here and here, now this region, yeah, indeed. Then the V over F constant, I can do this. But when the voltage is too low, right? No, we do not follow the VF. No, basically the VF equal to constant control. We don't follow that one. We change it. You know why? Because when the voltage is too low, now when the frequency is too low, now if you also reduce the voltage to a very low value, then you will lose no, because of the voltage drop in the stator. Then then you cannot get the current in the rotor. That's why you cannot get the magnetization, the current voltage actually. That's why we change it. We change it to constant voltage. So when the voltage, when the frequency is very low, much lower than this, now then we change the because of the stator impedance voltage drop. We call this a stator impedance voltage drop compensation. That means we do not follow this anymore. Now we just reduce your frequency by keep the voltage constant. Okay, so this is the variable voltage variable frequency. Yeah. Okay. Yeah, okay. That means the frequency is very low, below here. Then there's another part. Yeah, maybe what about the high speed? No, high speed also has a limit. Now, for example, when the frequency reach the rated frequency, which is also the rated voltage, right? Just now it's 415 phase voltage divided by square root of 3. No, you cannot increase the voltage anymore. Why? Because there's a insulation issue. The motor can get short circuit. So when you run your motor at a very high speed, now this high speed meaning goes to the right hand side, then we also keep the voltage constant. Yeah, you see, the theory of V over F control is interesting, needed. It's a generally applicable method. But when we use this one to the inverter, internally we have to consider the limits. When the frequency is too low, like the motor turns like a few revolutions per minute, then the voltage cannot go further down. You go further down, basically the motor will stop. Okay, then when the speed is very high, the voltage also doesn't follow, because if you follow, you go follow it here, then no, there's a chance, the insulation of the motor will break down, then you see the short circuit. Now this actually is the practical consideration when we apply the VF constant control method. All right, this one is the last one. Now you try to understand this one, right? You may see this one. I ask you to explain this real scenario consideration when you apply V over F constant control. All right, questions? Hello?
No
Yeah.
questions.
No. So
No question. No question.
so this part overall is this part has a lot of theory, right?
Yes,
Yeah.
correct.
Yeah, but this part is okay. Agree? This part you can explain, right?
Okay lah.
Yeah, this part is okay. Then yeah, maybe now you need to know this, right? Okay, so now I stop the recording. Now we take a break of now it's 8:30. Because I finished the lecture already. Now next in the second half, no, I mean in the following time, I try to go through some tutorial questions. Then you have a better understanding what is a V over F constant control. Is that okay? Because the lecture slides actually quite theoretical. I mean this no, a little bit abstract. Is that okay? So I stop the record. Then we not like some break. Yeah, it's quite 8:30. How about cause we have one break. How about 15 minutes? 1-5?
Okay, sir, can.
Yeah, 1-5 meaning when to come back. Now 30. Okay. 34 minutes, then plus 1-5. Yeah, it's about 8:50. Okay, so I stop the record. Yeah. I go here to stop it. Stop it. Okay, the recording. Yeah, stop. Yeah. Okay, so we take a break, okay. Yeah, around 8:50. That means before 9, we continue with some tutorial. All right, and I see you later.
Yeah. Please guide me.
哦，你看，你们也是好。
Hello, I didn't start the recording. Let me see. Yeah, I think some of you guys started the recording. Let me
Just now never stop.
Oh, but you see, this is interesting. Now go here, right? Now I do stop recording. You see, you can also see my screen, right?
Yeah, now can. Now there is this message from out. Just now don't have.
You mean you see the recording stopped?
No, just now never this
This
icon never
message,
appear.
right?
This
But
message never come out.
but something interesting, when I click on stop, right? Then the recording will start. Look, see? Yeah, recording has started by you. Let everyone know they are. Huh?
Mew, I think can stop.
Who? Yeah, because today I feel I'm not the owner. Yeah, never mind. Maybe just stop it. Yeah. No, don't stop. Then we continue. That's fine. So make sure this recording is there. Okay, so but anyway, you guys, someone that has taken over the control of these teams. That's fine. Yeah, that's okay. So okay, actually, next time, right before no, but next time you graduate already. I mean, next batch I will test this in the classroom because I feel Mr. Ng's setting a little bit different without the my right is not there maybe. Okay, never mind. Okay, just not hello. Yeah, all here, right? Let me check. Okay, now then next.
Yes.
Yeah, okay. Yeah, thanks. So next, right? The next one, about 1 hour plus, I will go through the tutorial questions, which is tutorial 6, AC motor control. More specifically is the induction motor control. Okay. So the second part is relevant, especially the question number 2, or you guys must know. Okay. Is it clear? Oh.
Roger.
Yeah, okay, Roger. Okay. Okay, great. Okay, fine. Then good. Okay, the first one, actually there are only two tutorial questions. Now, yesterday I didn't have no, I mean Wednesday I didn't have time to go through the inverter tutorial question. Now, we will do it in the classroom next week. Okay. Yeah, remember today's lesson, actually the makeup lesson, makeup online lecture. Okay, so there are two questions, question 1 and question 2, right? Question 2 is here. So the first one asks you this. Okay, before I start to talk about the question, you can see my screen, right? Can you see the screen?
Yes.
Yes,
Okay, good.
can.
Yes, good. Okay, so basically the question number 1 is a star-connected 3-phase induction motor. It's a star-connected 3-phase induction motor. Is driven by a 3-phase inverter. There's a driven by 3-phase inverters here. You still remember the 3-phase inverter, right? Yeah. How many switches you need to make a 3-phase inverter? You need 6.
6.
Yeah, 6. Also 6 diodes. Yeah, the freewheeling diodes. Okay. No, that operates with the ratio of voltage over frequency maintained at the constant. Basically, this one is the VF control, right? Yeah, it's VF control, meaning V over F. Oops. Meaning V divided by F is constant. Yeah, constant. Yeah, constant. So that's the control method. And more than that, no, also okay. The DC reels, no, the DC reels of the inverter are fed from a single phase 230 volt 50 hertz supply through a diode bridge rectifier. Okay, where is the DC reel? No, DC reel is this part. No, this is the DC. Yeah, this is the DC. But of course, we have a filter now, so that this part, no, wait. Okay, so that this DC is a constant one. Yeah, so this one. Now, also from here to here. Yeah, so this one is the DC voltage supplied by a bridge inverter, but no control. It's a diode. Okay, it's diode. Now, actually, then 250. The question asks you draw the circuit diagram. Yeah, draw like this. Okay, when you draw this, right? We add filter. Now this one, remember I said the inductor plus this capacitor that actually together behave like a low pass filter. That means the very low frequency, like a DC. Now DC frequency 0. The DC can get through higher frequency harmonics block out. So basically, this one is a typical filter. Now I can draw one here. Now inductor, then capacitor is a typical LC filter. Yeah. When your DC voltage here, remember the DC voltage from the diode has ripples, right? Then this positive DC goes through the inverter, goes through the filter, sorry. Then this side is more or less constant. Yeah. So this side, the right-hand side is a full, you can think is a pure DC. Okay. So that's part 1. You draw this. Okay. Now this one is the motor torque drives the mechanical load. Then the second part, explain the importance of applying constant V over F ratio control in the, okay, the reason is this now, constant VF ratio can retain the torque capability of the motor at operation below the rated frequency. Yeah, you remember I draw the one that looks like this, right? Yeah, you see it here. So this part actually can maintain the constant torque. Constant torque meaning the torque is always at the maximum. Yeah, you can maintain a constant torque. So this part is the VF gun. Basically, with this, right? You don't lose the torque, but otherwise the torque, because the torque is also proportional to the no the rotating magnetic field, because that one actually is related to the current. So, but anyway, that's the theory. This says, okay, why do we do this? Basically, we want to maintain the constant torque. Okay, then okay, that's part one. No, not much. Basically, drawing. Okay, then this one, okay, no, okay, everyone, this one, no matter what, you must know, okay?
Must know.
Yeah, must know.
Exam will come out.
Yeah, possible, very likely, right? Yeah. So this one must know. This one is the control. So everyone get the message, right? So this one is a must know question. Not very long. Not like no, I didn't give you the calculation like the formula one. You use formula to find this, find that, a lot of parameters, right? That one is a bit too long. But this one is not very long. This one is
but we must know how to draw, right? Is that the
Uh,
question that the A that what is stated in
draw
A,
this,
you need to
yeah.
draw.
I think it's good to know, but this one is a must. What I can say, this one, no matter what, you must know. Yeah, the drawing one, but of course you draw that, you know that one, which is also good. That means you know how to draw the diagram. That means you have a better understanding. But this one, the number 2, is a must know one.
Oh.
Okay, let's start. Okay, let's start to talk about this. Look at the question. Star connected, 5 kilowatt, 4-pole, 400 volts, 50 hertz, 3-phase induction motor. Basically, this first sentence tells you the rating, correct? Yeah, the overall rating of the motor on the nameplate. Yeah, so you look at the nameplate, you can see this. It's driven by a 3-phase inverter that operates with this is the key, ratio of V over F constant. Yeah, so under rated condition, under rated condition meaning the speed, no, under rated condition meaning the applied voltage is 400 volts, the motor output 5 kilowatts. That means that's the rated condition, frequency 50 hertz. Then the speed of the motor is 1,410 volt, 10 RPM. Okay, revolution per minute. Okay, the question is that you may assume the starter impedance of the motor to be negligible. Why? Because when we derive the V over F constant control, we have assumed the stator impedance of the motor is very small. It's negligible. Then we can get the conclusion, right? Okay, question 1. Calculate the rated synchronous speed of the motor. Can do or not? Can do, right?
Yes, can.
Yes.
Yeah, this one is easy. Okay, good. So basically 120, no, this is times, not x, okay, times 120 times 50 divided. Yeah, that's the synchronous speed, done. Okay, next one, calculate the rated slip speed. Okay, what is this speed? You remember, how do we calculate the slip speed? Now, basically, it's the synchronous speed minus the motor speed, right? This one is the synchronous speed. Now, this one is the rotor speed, the motor speed. The difference is the slip speed. Now, how to do it? You can just do a minus. Okay, the slip speed 90 RPM. This one is also okay, right?
Yes.
Yes.
Okay.
Yeah, so this part B is also okay. Then the next one, part C, calculate the rated torque of the motor, meaning the motor is running at the rated condition. Remember, P is rated how much? 5 kilowatts. Then omega is the, okay, actually the omega has a formula. The angular velocity is equal to, no, wait a minute. Yeah. Oh, the angular velocity omega m, this one is the motor one. No, actually it's equal to 2 pi speed. I use a small letter nm divided by 60. That's a formula. 2 pi nm. Okay, we just sub the value. P, now this gives you the omega m. Remember, the rated power, no, the output power divided by the omega m at the rated condition, you get the rated torque, right? Torque is Newton meters. So I just sub the values into here. Part 2, not much to do. Pi constant. Oh, this one is how much? This one is your rated speed of the rotor, 1410. Yeah, so I put 1410 here. Divide by 60. No, this whole thing gives you omega m. Okay, press your calculator. Now this is times again, not x. Right, I said. And then press your calculator, you get the rated torque of the motor, 33.86 Newton meters. How about this part? How about part C? Is it doable?
Easy.
Okay, good. So I take easy. It's also easy, right? Yeah, take. Okay, so we got this. Okay, great. Remember, the slip speed at rated conditions 90 RPM. Yeah, remember this. Later on, we use it because we are doing a V over F control. You know, the slip speed is always constant. Okay, great. Then we go to the fourth part. Okay, the fourth part is this. Now they say, okay, now if the motor torque remains at the rated value, the torque is at the rated value. How much is the torque rated value? 33.86, right? So that's the torque rated value. And the motor is required to run at 1,200 RPM. Question, what should be the inverter's output voltage? Yeah, so they ask you the inverter output voltage. Correct. So this one, you have to look at the solution now, read the solution a few times, then you can figure out how to do it. Okay. Now this diagram now is when you do this, you don't have to draw this. Basically, this part tells us how do you find the new output voltage. Okay. Now first, now you see, okay, now when the frequency is 50 hertz, right? What is the slip speed? Slip, okay, write down. Okay, wait, I write a better one. Okay, at 50 hertz, what is the slip speed? How much is it?
90.
Yes,
90.
great. Yes, great. 90. So it's 90. Meaning between here and here is 90. Yeah, this is 90. Yeah, this is a 90. Okay, now we change the frequency, right? Because the motor slows down. So the frequency becomes smaller. Then we shift the curve to the left. So you get the new torque speed characteristic. Okay, the load is constant because the question says the load maintains constant, right? Yeah, no change. Okay, now the frequency reduced. So you get a new motor speed is here, right? But remember the theory says at the new frequency, no, the slip speed is the same. That's the theory. Now this is also 90. Okay. Now from here, actually, you can find the inverter frequency, correct? Okay, let's see how to do it. Okay, so this just now is the analysis. Now we do the calculation. Slip speed 90, true. Then therefore, at the same rated torque is the same. The slip speed will be the same as for the case of 50 hertz. That basically this, here's 90, here's also 90. Yeah, why is this? Because this is the VF constant control. Is that clear? Yeah, so basically same. Okay, then we can find something interesting. So therefore, the speed here, right? The speed here, how much it should be? The speed here. Now this is synchronous speed here. The new synchronous speed. How much is it? If I know here is 1,200 and the distance here is 90, can you find this one? Yes, just add. True? Yeah, that's the one. Is that right?
Yes.
Yes, correct.
Yeah, correct. Because you told me the VF control always gives you the same slip speed, right, with the constant torque. So yeah, I'm using this theory. Okay, got it. Okay, then from here now, actually this one is the new synchronous speed for the frequency F1. But we know this speed, right, is also equal to, no, this speed is also, no, the speed here, the new one, I call it, actually here we use NSF1, yeah, quite long one. Maybe I just use N1. No, remember, N1, remember this formula, 120F over P, correct? Then, okay, this one we know, 1290. How many poles? 4, right? The question says there are 4 poles. Yeah, you see the question again? Yeah, 4 poles, written here. So it's a 4 poles. So I sub the 4 poles here. Then cross times. Now my goal is to find the frequency, correct? Then from here you can get it, 43 hertz. Okay, now it's very clear. Actually, no, you know what? You want to run the motor at a lower speed, 1,200 RPM. No, your frequency should be 43 hertz, not 50 hertz anymore. No, here it should be 43 hertz. Yeah, 43 hertz. Now, why? Because now the motor turns slower, right? Compared with just now the 50 hertz, the motor has to slow down a little bit. Yeah. How much slow down? Actually, it's from your 140 slow down to 1200, 1200. Correct. Okay. So I get the frequency. Okay, one more step, you can find the voltage. Remember, V over F constant, right? So your V 400 volts, rated value. Then your frequency is 50 hertz. Now I don't know the voltage here, but I know the frequency 43. Now this one is 43 hertz. Then sub into this equation. Now you look, doesn't matter where your voltage is. No, doesn't matter where's your frequency. But the frequency is not very low, but for extremely low frequency, like a few hertz, 1, 2, 3, 4 hertz, then we have to change the control method. Remember, from the constant VF, change it to a constant voltage. But here, 43 hertz is quite far away from the very low frequency, usually few hertz. Okay, then we do a cross time. Now look, the rated one, the constant ratio, when you run the motor at constant rated condition, you get the constant ratio. Then for the new operation F1, then the ratio should be the same. That's why we can equal them. No, these two, we make them equal. From here, you do a cross times, then you can find 344 line voltage. Now, interesting. So you see when you do 50 hertz, what is your voltage? Now 50 hertz, you need voltage 400 volts, right? Now you lower down, you want to slow down the motor. You lower down the frequency to 43 hertz. Then how much is the line voltage? 344. Okay, the problem solved. Yeah, any questions? I pause here for a while. Any questions? Is this part doable or not? Easy or very hard?
Formula given.
Which formula? You mean the ratio? Let me see. Let me see the past paper. Now, by the way, because Mr. passed me some past paper. Marking guide. This one is 2024, right? Yeah, 25, 24. Let me check what formula given. You can also get the past paper from the website. Rectifier, you see. No, let's go to the motor one. See the DC chopper also. No, this one is to calculate the no, the ripple. Yeah, let me see the induction motor. Oh, yeah. Okay. Now these are the induction motor formulas. See what is given, what is not given. Oh, this one is given actually. Synchronous speed. Synchronous speed is given. The slip is also given, you know. Right? Oh, okay, what? Then these are the only two formulas given. Yeah. So the ratio one no is not given, but you are given these two. Is it clear? Yeah, not all actually, but only two. Yeah. So go back to the Yes.
Can you explain the V over F again? The V
view
rated
rates again.
over
Okay.
RF.
Yeah, go back to the question again. Okay, that means the formula. No, let me finish the formula. The formula part. No, the formula this is not given, but this one given. Yeah. You mean this one again, right? Or the frequency?
Yes. Can go through like one more time, a quick one.
Yeah, sure. Okay. Now, you know, okay, good. Let us go back to the question again now. If the motor, okay, the question D, because just now the motor runs at what speed? It's 1410, isn't it?
Yes.
Yeah, okay, good. But now I'm not happy with the 1410 RPM. I want to slow down a little bit. Slow down to what RPM? To 1200. Now that's the goal. I want to make my motor slow down to 1200 RPM. Then because the motor is driven by an inverter, then he asks you, hey, tell me if we use a V over F constant control, then what should be the inverter voltage? So that's the question, right? Then through the calculation, we know actually eventually your answer is here, 344 volts, right? But question, how did you get here, right? Okay. So the theory is this, when the motor is powered by a 50 hertz supply, you have the slip speed 90. You know how to get the 90, right?
Yeah.
Difference now. You see from the previous example, it's from here, you see. I take, I say you have to remember this slip speed, right? Yeah, from here. So at 50 hertz, yeah, we get 90 RPM. But what is interesting is, okay, now I reduce, because your motor slows down, you have to reduce the frequency. But if we use the VF control, actually something interesting, your slip speed will remain the same. That means, go to here. No, this slip speed will be 90 also. Yeah, can you accept this point or not? That's the theory. That means here is 90, the rated condition. But now the frequency is lower, it's lowered down, but the distance here is still 90. Yeah, that's the magic. That's why, because of the VF control method. Okay.
Okay.
Yeah, okay. Then now once you know this slip speed is 90, then plus the motor speed, you get the synchronous speed at a new frequency, right? Yeah, basically you add. So we go back, we can tell, oh, if your motor speed now runs at 1200 RPM, now with the constant slip speed, no, your synchronous speed must add them together 1290. Okay, so this one is quite easy, né? 120 plus 90, right? You get the speed here, the synchronous speed is here, right? Yeah. Okay, that's how we get the synchronous speed. But don't forget, synchronous speed is also follows this equation, correct? Yeah, because this one actually, remember, they give you follows this one. Yeah, this is synchronous speed. Yeah, also follow this. Yeah, so you go back, use that one, you can find the frequency 43 hertz. Is it so far so good?
Okay.
Okay. Yeah, okay,
Good.
fine. Okay, once you get the frequency right, then we apply the theory. Remember, your V over F should be a constant value. Constant. Oops. Yeah, constant. Constant value. Okay, that means when the motor is driven by a 50 hertz inverter, you get a ratio, right? Remember V over F. But now I have a new frequency. I also get a V over F. No, these two should be equal. Yeah, that's why you get here. Remember, 50 hertz is the rated condition, is 400 over 50. Then it should be equal to the new one. Now here, so it's V1 over F1. But your F1, you found it already here, now 43 hertz. Okay, now you sub your 43 here, do a cross multiply, then you can find the voltage. Done.
Okay, Ken. Thank you. Thank you.
Okay.
So if next time this kind of question, just the old one equals to the new one lah. Then do
yes.
algebra, then we get the voltage lah. Correct or not?
Correct, correct. Yeah. Because that's
Okay.
because that's the control, you know, V over F, constant. Yeah, that's the control method. But if you use other control method, no, cannot do this. But we don't discuss other control methods. Okay. All right.
Can go home already.
No, wait, there's another part. There is a E, you know. Yeah, there's a part E. Yeah, okay. So this question actually has how many parts? A, B, C, D, E, 5 parts. Okay, now the last part actually says, okay, calculate the motor speed. Now calculate when the inverter output frequency is 30 hertz and the motor is operating at 50% of the rated torque. See, cannot go home yet, right? Yeah. Yeah, okay. So the question is, okay, now, no, the difficult part is here. Okay, at the beginning, the torque is here, right? That's the rated one. No, the zero should be somewhere. No, wait a minute. I think I should draw a straight line. Now let me draw a straight line. Oh no, I tried to draw a straight line. Okay. So at rated torque, excuse me, it's here. Oh no, the axis is here. No, the axis is here. But now you lower down the torque to half. Yeah, that means between here and here they are equal, right? Because 50%. Okay, let me try to draw a better one. Okay, make it more like a reasonable one. Yeah, okay. Now maybe this is no, too low. Okay, too low. Because my mouse is not very easy to control. Yeah, I got it. Roughly see here. I got it. So you see, I'm still not happy with this. Okay, roughly here. Okay, that's the line. Okay, now you see, here is a full load. Now your two things have changed. No, one is your inverter frequency is smaller. Yeah, 30 hertz is lower than 50, lower than 43, right? Just now you get it. Then the other things, no, there's another parameter also changed. What is it? The torque has been halved. So the new torque is here. Okay, the new torque is here. So basically from here to here equal, isn't it? Because half, this and this is equal. Okay, then based on this, right, they ask you, hey, calculate the motor speed when the inverter frequency is 30 hertz. That means 30 hertz is something like this. Okay, now when you do the question, you don't have to sketch this, because this one basically to help us to understand what is going on here. Okay, so just now remember 50, no, the full load, right? From here to where? 50. Okay, the drawing is not very accurate. I actually should go down a little bit more. Okay, now never mind. Give me some time. I do this one. Should go lower down a little bit more. No, actually should go here. Ah, this one is better. Okay. Okay, but I have to extend this to here. Okay, now this is very critical. You remember? Now, if your torque remains constant, right? From here to here, how much is it? Is it 90?
Yes.
Yes, right. Yeah, yes. Yeah, you're right. Yes, 90. But now your torque has been lowered down by 50%. That means you lower down to here. So now actually the 50% is here. So the question is this. Then how much is the speed between here and here? Okay, now because your torque is halved, right? Now we assume this one is a linear one. No, okay, I draw a better one. You see, like this. Okay, okay, like this. Oops, no, this no, I'm not happy with this one. All right, so okay, now this between here and here, how much is it? Okay.
90.
Answer this. Okay, guys, and answer. How much is it? 90, is that right?
Yeah.
90. Now, but this one is for full load. Now the full load torque is here and the full load. But now you have the load. Then the question is, how long is it from here to here? Okay. Now this one actually is proportional to your decrease of the torque. Now, if your torque is halved, so the angle is also no, the slip free speed is also half. So this one becomes 45.
45 half, is it?
Yeah, half. No, why? Because this is, for example, is the whole half, not the full torque, right? This one is half. Then this is the full one. Then this one is half. Basically, it's the similar triangles. Yeah, is that clear?
Okay.
So yeah, so this now when this one here, for example, is 1, I just say it's 1, then this one is 0.5. Okay, then same thing. Now here is 1, then this one is half, but your 1 is 90, isn't it? So this small one, the base should be 45. Yeah. So once we work out the slip speed, the following part actually is quite easy. So it's 45. Okay, then we go back to the same thing. Therefore, synchronous speed at 30 hertz. This one is the formula you should know, right? Because just now I heard yes, this one can be done, right? Yeah. So this one is 900 RPM. This one is the synchronous speed when the inverter is running at 30 hertz. Okay, then because your slip speed is halved, that means meaning the motor speed the synchronous speed minus the motor speed, you get how much? 45. Okay, from here, you can get the motor speed, and you see, now this one is synchronous speed minus the one I don't know. Then from here, you see, move this one to the right-hand side, this one to the left-hand side. There you go. You get the motor speed. Done. Interesting, isn't it? Okay.
Yes, very.
Very, very.
very, very, very. But you get what is going on here.
Yeah, so when they
Yes.
mention motor torque, right?
Ah,
Motor torque means it relies heavily on the slip speed, is it?
the
Correct or not?
motor. Oh yeah, you can say that. Actually, the motor torque determines the slip speed.
Alright. So whenever the motor speed changes means the slip speed also changes lah. Correct
No,
or not?
whenever the torque changes.
Okay, can.
Whenever the torque changes, then the slip speed. Okay, the keyword is the slip speed. Yeah. So wait a minute. I get sometimes my mouse is not very responsive. Now you see the keyword is the slip speed. It's not the S. It's the speed difference between the synchronous speed and the motor speed. You see, we divide by 2. Okay, it's here now. You see, we divide by 2. Why divide by 2? Because your torque now is only 50% of the full load torque, meaning you have divided your full load torque by 2, correct? You only 50% left. Yeah, questions? This one, you have to study this, carefully, because you need it. Yeah, when you do, questions or maybe tests or something. Yeah.
So you
Okay.
got more exercise paper for this, so we can.
I don't have. I cannot show
have,
you the test. Cannot show you the test paper today. I don't
No,
have.
not test. You got any exercise question so we can learn?
Oh, I don't have. Actually, this one is a very good one. Now, maybe you assume the answer is not there, then you go through this one more time. Not so many parts, from here to here, 3 pages, right? 3 slides. Maybe you pretend the solution is not there. I just want to do it myself. Then you redo this one more time. Actually, it's a huh?
Sorry,
Hmm.
this part of NS30 minus NN30 equal 45 RPM. This part, can you just slightly explain one more time?
You mean this one, right?
Yeah, NS30 minus NN.
Okay. It's a good question. Okay, let me erase this.
NS30 is the 30 hertz. So the 120 is actually the fixed figure times F. Then
Sorry
underneath
again.
is a 4 pole, correct?
Oh yeah, no. I think his question is this one, not the synchronous speed. Is the no? This one I think you okay, right? No, this one okay. This one is the synchronous speed when the frequency is what?
Yeah, okay.
Sorry,
the lower part.
Yeah,
30
hertz.
hertz.
It's only the lower one. Yeah.
Yeah, only the lower one. Okay.
Yes.
So you remember now the difference is here, right? Now you see here. So this one is your is how much is here? 9. Now this one is 900. Okay, here. Then what is your motor speed? We don't know. This one is the motor speed. We really don't know, right? Yeah, this one is you don't know. But do you know how long is this between here and here?
45.
You know, right?
45.
45, right?
Yes.
Yeah, then,
that's how you get it.
Then 900 minus 45, you get here.
Okay.
Yeah, that's
So
the
we
speed.
based on assumptions. This is more like assumption based on that. Right.
What do you mean? Yeah, go ahead.
Because of this assumption that there's 50% reduction, that's why 900 plus 45. That's why the answer is 945 RPM for the new speed.
Correct. So the VF control, one advantage is the slip speed is always constant. When you lower down your torque, right, you have to reduce the slip speed correspondingly. No, you see, I draw the small part is something like similar triangles, you know, it's a proportional. Yeah, you lower down by 50%, this one also 50%. You lower down by 2/3, no, this one also goes 2/3. You see, if you lower down more, right, you know, this one becomes also narrower, isn't it? Yeah, so you go up, then go up here. Okay, so
Okay,
that's
okay.
the
Thank you.
whole story of induction motor control using V/F constant method.
So the question,
Mm.
like this question, they say like sleep speed is at 50%, where we know half of it. There are cases where they put 70% or
Okay.
there will be difference.
No, just now I said, you know, if this one is 70%, no, this one correspondingly, you also have to do 70%. That means the 90,
Okay,
you know, this 90 RPM, you have to do it correspondingly. Now 50%, then I times 50 here. 70%, that means you times 70 here.
Oh, okay. So like
Ah.
80 just times the 80%.
Yeah, 80 is 80%. 100% no change. 100% is a full load.
Okay, thank you.
Yeah, no problem.
Bye.
Yeah, okay. Any other questions? No, now it's weekend actually. But anyway, tomorrow. Can go over, yeah. Tomorrow is a Saturday night category. But actually, you know, Nian Poly now we have open house. Actually, tomorrow I have duty 4 hours. Okay. Yeah, so you will be tomorrow. The Nian Poly campus will be will be a lot of people there, and you can see a lot of people, parents, students, and yeah. Okay, that's all for this one. No worries if I still not completely sure about this part. You can take your questions to the tutorial lesson next Wednesday, right? No, it's a fifth. Next Wednesday is I need to check with Mr. Is it tutorial or practical? I need to check next Wednesday, 14th. Tutorial. So we do 5 and 6. 5 and 6. Yeah, but actually, no, this one is 6. Then there is one more topic. Maybe in the tutorial I go through the other one. Remember, there's also a little bit left in the. That's the last topic. Topic 7, AC application. You know how to do the. For example, a dimmer or heater or something, how to do that one, how to control that one. Now that's the last one. Okay, we have done our job. Maybe you still have questions about the inverter, maybe. Then fine. Then next Wednesday we can we go through this together again, focus on the tutorial questions. Then I think the things will be much clearer. Yeah. Okay.
Okay.
Yeah. Okay, then good night, everyone.
Hey,
Tomorrow
recorded.
campus got makan
Tomorrow, sorry.
Campus got makan
Oh, Macau, no, I'm not very sure. But if you know for example, your friends, whoever have this age of kids, right? Then you encourage them to come here. I think you will get some gift. Yeah.
Oh, okay.
Okay. Yeah. Now you are also welcome to come back, because I think the open house is not only to teenagers, it's also for the working people like us. Yeah. Okay.
I do the open
Okay, see
house,
you
not
tomorrow lah.
orientation.
Yeah.
Orientation time got free makan.
Oh, really? But now I'm not very sure we have a free maga or not. I really don't know because tomorrow my one is morning 10 to 12, 12 to 2. So my duty is actually across the lunchtime. Hopefully there will be something to eat, but otherwise I have to go somewhere. Yeah. So never mind. I think these were very interesting. I talked to parents, to young I mean the would-be students, quite interesting.
Hey, we try to stop the recording and see whether it records or not. It stopped.
Okay, no, to be honest, I don't know who is controlling the recording.
This Mio. You see whether you can stop recording?
Should be now is controlled by him. Let me take a.
You try. Because my side cannot.
I also cannot see.
Let me
disable.
stop it. Yeah. Yeah. As a start, no, the recording indeed is, no worries actually. Now, if something wrong, no, we didn't record properly, it's also okay now, because we have a few more like, okay, now you see what I'm trying to do. I stop recording. Okay, looks good, right? Stop recording. Stop.
Stop.
Yeah, you see, start again.
Mil, you cannot stop, huh?
Not from here. Let me take a look.
Who takes, it seems like